All right, so want to look at some example problems. Here's the first one. So we have a scale being used to weigh fish. It has a spring connected to the end of the ceiling, so it's always a good idea to have kind of a picture in your head. So we have this spring here, and the spring's equilibrium position is 30 centimeters. And then when a 4 kilogram fish is suspended, the spring stretches to a length of 42 centimeters. And that's when we have a 4.0 kilogram fish on it, okay? And then if we look at the questions, it wants us to find the spring constant K. And then it says if an 8 kilogram fish is suspended from it, what will be the length of the spring? So the first thing to recognize is if this was an actual AP problem, they would not ask you question A most likely, unless it was in the free response. If it's a multiple choice question, they will not ask that. But you cannot answer this question without it. Well, I guess you could find a way to do it without actually solving it. You do it algebraically and eliminate K from the problem. But in general, finding the spring constant is often a step that's needed. That's not necessarily specifically tell you to do that. And they'll give you information like kind of did here. Like this intro information is actually what we need to use to find K. And then the actual problem is here. So if this was just all one big thing and it didn't ask you to find K, you probably would need to find K somewhere along the way or find a way to eliminate it algebraically from your solutions. So if we wanted to find K, I know that my spring force is equal to K times my displacement. In terms of magnitudes, I'm not worrying about directions. This is not the vector form of this equation. This is the magnitude version of Hooke's law. So the first thing to recognize is it's always based on displacement. So displacement is x2 minus x1. So you don't ever want to just say, oh, well, how far did it go? I always want to use the difference in the positions. I'm not ever using absolute positions. So in this case, my displacement is 12 centimeters. You went from 42 centimeters to 30 centimeters. And, well, what's the spring force? Well, I know here that when it's here at the bottom, that gravity is pulling the fish down and that the spring force is pulling back up. And that when it's hanging here at the bottom, the gravitational force equals the spring force. Now, that's not true in this intervening time where you have the springs still moving. It's only true essentially at this endpoint, but that's fine because we're not looking for work. We're not looking for potential energy. We just want to know what is the spring force right here to keep that 4 kilogram fish at 42 centimeters at a stretch of 12 centimeters. So if I want to solve for K, K is going to equal my spring force over x2 minus x1, but that spring force is going to equal my gravitational force. So because my gravitational force, my spring force minus my gravitational force would equal 0, because my net force, so those have to be equal to each other. And my gravitational force is m times g over x2 minus x1. So if you go and you sub in numbers, we get that m is 4.0 kilograms, G is 9.8 meters per second squared, and then x2 is 42 centimeters minus 30 centimeters. And we end up with a spring force that is going to equal 330 newtons per meter. So we have that there. Now, I did this in meters. When you actually do this calculation, if you leave it in centimeters like this, you're going to have a problem because the units here are meters, whereas the units down here are centimeters. So although this is a difference of 12 centimeters, it's a difference of 0.12 meters. So you need to make sure that you're always double checking your units. K doesn't have to be in meters. I could have reported this in newtons per centimeter, but that's a little weird. But it is something that you could see. You could see K values represented in newtons per centimeter, so you need to watch out for that. So that was part A. So we found out that K is 330 newtons per meter. Like I said, I just rounded 2 sig figs on that. So then if we wanted to find the next part, now what's happened is now we're going to put an 8 kilogram fish on. So we know that if I have a bigger force, that it's going to cause it to stretch. So that I'm going to have this ugly looking fish thing here. That didn't quite turn out. It's a fish. That we have an 8 kilogram fish suspended for the spring. We want to know what will be the length of the spring. Well, at this point, we're still going to have our gravitational force equal to our spring force. Because we're going to be in equilibrium at this point, but we want to know what is the length of the string. So we want to know what is L equal to at this point. So what's our length of our spring? Well, we know that our spring force is equal to K delta X. We found K. We know that our gravitational force is going to be M times G. And basically our delta X here is going to be L minus, if we wanted to call this x0, which is what with the symbol we normally use for the equilibrium position, minus x0. So if I wanted to solve for L, I'd have to do mg over k, and that's going to be L minus x0. So L is going to be mg over k plus x0. Then what we're going to want to do here is we're going to have m is 8.0 kilograms times 9.8 meters per second squared over K. So K is going to be our 330 newtons per meter. And then we want to add in x0. So can I, in this case, keep it in centimeters? Well, no, because if we look at our units, our unit for Newton is based on meters, and we've got meters here. So we're going to need to actually be in meters. So 30 centimeters is going to be 0.30 meters. So that is going to give us an L that is equal to 0.54 meters. And that 0.54 meters is going to result in an L equal to 54 centimeters. So that would be our length. Now it's important to note that even though we doubled the mass of the fish, we did not double the displacement. You ended up with a displacement of 12, and when we added another 12, so a displacement of 12 for 4 kilograms, we have another displacement of 12 for 8 kilograms. So actually the extra added displacement just added the same amount. We didn't double the amount of displacement. So you have to be really careful with that, with making kind of predictions and things for happening. Now this is actually how a spring scale works. And I don't have one here while I'm making the video, but basically the way a spring scale works, and you've seen these in some of the videos and so forth, is it has markings on it. And the markings are often in newtons, but there's sometimes also markings that correspond to grams. And basically there's a spring inside, and there's some sort of line marker based on that is connected to essentially whatever you're hanging it to. So that way, when I put a mass here that has a gravitational force, when I hold it at equilibrium, it's giving me a spring force here that's equal to the spring force in the spring scale. So that the scale is going to stretch the spring, and the scale markings are made so that it knows how far the spring is going to move for a particular force that is applied. It's been calibrated specifically for that. And as the springs get stretched or older, you're using a horizontal versus vertical, most of these have a means for you to calibrate it by basically shifting the spring a little bit up or down to line up with the marking, so you can actually zero it out at the start of your situation. And then you can figure out how that kind of affects how things go. So the fact that this was 12 centimeters every 4 kilograms would give us a means to set up a scale where, hey, every 4 kilograms, I need to have a marking, so there'll be 12 centimeters of difference in that stretch. All right, so we're gonna take a look at this example. It's a little similar to the one before. This is more typical of what you'd expect to see. So you have a 1 kilogram weight suspended from a spring, stretching it by 5 centimeters. How much does the spring stretch if the 1 kilogram weight is replaced by a 5 kilogram weight? So you're gonna have this spring here, and you're gonna have basically with this 1 kilogram weight here, you are going to have a stretch from some equilibrium position of 5 centimeters. And we can assume that when it's at this position that you're going to have that spring force that is perfectly balancing out the gravitational force. So if we were to write a net force equation in the y direction, we're going to have our that was supposed to be a spring force there, sorry. To write our net force equation, you're going to have spring force minus the gravitational force is still going to equal 0. So our spring force is going to equal the gravitational force. And I know that my spring force is K times delta X, and my gravitational force is M times G. So what I know is that in these two situations, in the situation with 1 kilogram and the situation with 3 kilograms, that K is a constant. Now in the previous example, we actually did find K. In this case, it's not asking us to find K. We actually don't need to. We could, but we don't have to because I know that K is constant. So if I solve for K, K is going to equal mg over delta X. So K is going to be the same in both cases. So case 1, I can say that K is equal to m1 times g over delta x1. That's this case. And then I also know that that's going to equal m2g over delta x2, which would be the case with the 3.0 kilogram weight. And I can see actually that g is also a constant, so g is going to cancel out. So if I wanted to find the new stretch, which would be delta x2, let's see, if I cross multiply, I'm going to get delta x2 is going to be m2 delta x1 over m1. So without even finding K, I can find my new stretch. So delta x2 is going to be m2, which is 3.0 kilograms, times my displacement 1, which is 5.0 centimeters. In this case, I can leave that as 5.0 centimeters. If you're worried about unit things, you can always convert to meters. That's safer to do. But in this case, I know that my answer can be in the same unit over here because my mass units will cancel out. And then m1 was 1.0 kilograms. So my new displacement is going to be 15 centimeters. So you end up with getting the displacement there. So this is a standard like problem that you would see on a multiple choice section, quiz, etc. Kind of like on your homework. All right, this problem is a little bit different. We have a non-equilibrium situation here. So we have a 25 kilogram child bouncing on a pogo stick. The pogo stick has a known spring constant. And then the child is going to make a big bounce. She finds at the bottom of the bounce, she's accelerated upwards at 9.8 meters per second squared. And we want to figure out how much is the spring compressed. So if I was to kind of picture this one, I would picture like a pogo stick here. I'm going to assume that there's like a spring here. So basically what this is saying is that during this bounce, basically because she's standing here on this pogo stick, that there is a gravitational force. Really technically it's the kid's normal force, but we can assume that the normal force and the gravitational force are related. And then that gravitational force here is being resisted by a spring force upwards. And that this spring has been compressed by some amount And that's what we're looking for. But it tells us that there's an upward acceleration equal to 9.8 meters per second squared. So if I was to write my net force equation in the y direction here, my upward force is the spring force. My downward force is the gravitational force. And then that's going to equal to m times a. Now, my acceleration is upwards, which is the same direction of my spring force. This tells me that my spring force is actually larger than the gravitational force. Now, I know that my spring force is k delta x in magnitude. My gravitational force is mg, and then we have ma. So I'm looking for my displacement, delta x. So I solve for displacement and add the mg. And then I'm going to divide by k. So I get delta x is going to equal basically m over k times a plus g. If I do a little algebra rearrangement there. So I'll pull out the m and then divide the k over. So this tells me that my displacement is going to be the mass, which is a 25 kilogram kid, over the spring constant k, which is 2.0 times 10 to the 4th newtons per meter. So that is a pretty large spring constant, which makes sense for a pogo stick. And then you're going to get a plus g. Well, a is a positive 9.8 meters per second squared. G is a positive 9.8 meters per second squared. Remember, g is a scalar value. It is not negative. The acceleration due to gravity can be negative, but g itself is a scalar value. So when you calculate, you get a displacement of 0.245 meters for that one. So this is a problem that I've seen people get wrong. The most common mistake is actually having some form of subtraction here at this point. And so you end up with a value that is smaller than what it's actually supposed to be.